So continuing the normalization, now I'll tell something very interesting. So in my previous lectures, what I've done is I compared this psi, which is an amplitude, with the amplitude of say light, say electric field, and I said that the probability, which is nothing but square of psi, and I related this with the intensity of light. And then even after I made this comparison, I said that psi must satisfy this normalization condition. Now something very interesting happens. If you look at the normalization condition, then you see that this part psi dx. So there is a psi dx on this part with an integration, and this side we have just a number, and this number has no units, so it is unitless number. That means this part must be unitless, or this part must have no unit. So can you guess what will be the dimension of psi? Now since the dimension of dx is length, so dimension of dx is length, to make it dimensionless, the psi must have a dimension of 1 by length. Okay, this is quite something very interesting. Now, so this is the dimension of psi. However, this is contrary to the amplitude in case of wave. For example, in wave, if you have a wave generated on a rope, then you know that y, which is a wave equation, is already is written as y is equals to a sine. Okay, and we have a omega t minus kx. Okay, this part is dimensionless. This part has a dimension of length. This part has a dimension of length. So the general wave equation of a rope has a dimension of length. However, on the other side, this wave equation in quantum mechanics have a dimension of 1 by length. So in the next lecture, we'll talk more on quantum mechanics.